I don't have top 5 stories. I was joking. Top 5 story. Devin needs to put her food away. There you go. All right, story number 1. Shh. Okay. Now, we will reference this picture if you guys need to, or this picture if you guys need to, but I think we're ready to move on from it, and we'll start by this. I am trying to find the area beneath x to the third from 0 to 3. If you were to graph that, I'll sketch a quick little graph. That's your area that you're going to find. I'm going to show you after we do this example how to verify your answer on the calculator. It'll happen just like that. It'll be very, very cool. So we're going to skip doing 4 rectangles because we've already done that, and I think you guys are ready to move on to the bigger and the better piece. What is the width of this interval? 3. So if I divide it up into n rectangles, what's the width of each rectangle going to be? 3 over n. 3 minus 0 divided by n, which is 3 over n. Very good. Now, so what we're trying to do is this piece right here. So we've got to get set up for this. I've got this delta x, which is 3 over n. That's the width of each rectangle. Now I need that x sub I. That's the point at which we evaluate each one. So that first rectangle, will we evaluate it at 0, or will we evaluate it at the first width? The first width. And to get the first width, what I do is I take the beginning value of our interval and I add it to the width times I. So, like the first width, I would put I equals 1. The second width, I equals 2. So on and so forth. What's the beginning spot of our interval? 0. So I have 0 plus, the width is 3 over n times I. Now it's going to change because the fourth problem you have is from 2 to 5. That's where we're finding the area. So it's totally different. It's a lot harder. All right, so we've got the width is, the spot where we evaluate them is 3i over n. Now we can express the area as a definite integral. Definite means it's bounded. So we draw this symbol. That's an integral sign. What number goes on the bottom? 0. What number goes on top? What function goes in the middle? X to the third. Then what do I put? dx. That's shorthand for writing all of this. Limit as n goes to infinity of the summation from I equals 1 to n what? That's my first rectangle. So we're gonna do the height of the first rectangle, then the second, then the third, then the fourth, and that's what all the way up to infinity. Infinity. I plug in the spot where I'm evaluating it into my function. It says f of x sub I, right? So I need to take that 3i over n to the third power. So that's f of x sub I. If we had 2 different x's, like in the next problem, you got to plug in, that twice. Times 3 over n. That's delta x. Isn't it pretty? Because you don't know what this means yet, we are going to take this, and I'm going to show you how to do this in about 5 seconds. Okay? Next week, you're going to see this. You're going to know how to figure out this area just like that. Just like when you learn how to take the derivative of 3x squared to get 6x, and you're like, oh, wow, that's easy and that's cool. Same thing's going to happen. Okay, I'm going to show you how to do it. Right now, we're saying this is equal to this Riemann sum, and this is what we're doing. So let's simplify this. What's 3i over n to the third? Very good. So I got the limit as n goes to infinity of the sum. 3 to the third is 27 times 3 is 81. So I have 81 I to the third over n to the fourth. Awesome. Well, 3 to the third is 27 times 3 more is 81. Now what I'm going to do is I'm going to factor out the 81. Question? No? I'm going to factor out the 81 over n to the fourth. So I have the limit as n goes to infinity of 81 over n to the fourth times the sum from I equals 1. I forgot to write that up there, sorry, to n of I to the third. Now, just to understand notation, if I'm going to let this go to infinity, I got to have n's, right? But I don't. I've got i's. So, yes, Ina, I grab one of those things. And we prove that that's true by, starts with an M, mathematical induction. So I grab the I to the third piece, and that's where I substitute my known sum in for I to the third. So this sum of n integers cubed is going to be the limit as n goes to infinity of 81 over n to the fourth times n squared times n plus 1 squared all over 4. Bada bing, bada bam, bada booski. All I have left is an infinite limit. You know how to do limits as they go to infinity, right? So let's just work out the algebra, and away we go. Ooh, then we would have to do math induction and figure out a formula. That would be really bad. Yeah, well, no, you bring up a really good point, Derek, and that is, what about these problems here that, I to the third? Well, what about I to the fourth, I to the fifth, I to the sixth? Well, what about sine of x? Let's forget about powered polynomials. Let's start thinking about trigonometry. Then we're kind of in, we're up the creek without a paddle. That's why I'll teach you calculus. Okay, let's do it. Limit as n goes to infinity of 81 over, we have 4n to the fourth times. Up top here, I'm going to have n to the fourth plus 2n to the third plus n squared over 1. Everybody see how I got that? And that's why you're in this class, because your algebra is so good, right? You can just flip through and do that. So I squared the binomial and I distributed the n squared through. I got that. What do I factor out of the top? So the limit as n goes to infinity of 81 n to the fourth times yes, you have to write this step down. Why? Because I said so. All right. 1 over n squared goes to 0. 2 over n goes to 0. n to the fourth over n to the fourth. You're left with 81 times 1, which is just 81 over 4. That is the correct answer. We just summed an infinite number of rectangles to come up with the exact area underneath the curve bounded by 0 to 3. That's amazing. Amazing, you guys. And we did it relatively quickly. It's not even 10:30 yet. What? Oh, gosh. The economics applications and the applications to physics and science are endless. When they were able to put this into mathematics and utilize it, I mean, I don't even know where to begin. I mean, we wouldn't be in space without this. When will you use this in real life? You might not. You might not ever, use what we would refer to as the definite integral. You might never use it. But is it utilized daily? Yes, without a doubt. Without a doubt. And we'll get to some of the applications in a little while. Right now, you guys need to see the raw nature behind it. Actually, adding up an infinite number of rectangles? No, nobody ever does that anymore. I mean, that's just, nobody ever does this. That's absurd. That's like Dark Ages stuff, okay? We know how to do calculus now. We don't know how to do it. So why do this? Builds brain power. You're becoming smarter. Watch. I'm gonna allow you to grasp it right now, and it's not gonna be as bad as you think. You guys only see the algebra. Start thinking about the geometry. This is the shape of the curve, right? And this is the area. Just tell me this. The area bounded under this curve between these two lines, is it an infinite area or is it a definite area? It's a definite area. So we've established that, right? Second of all, can I divide this up into an infinite number of rectangles? Well, sure I could. What's the width going to be of each rectangle eventually? 0. I mean, it's going to get very small. The trick is, and what makes this all work, is that what we do is we say the width is actually going to be b minus a over n, which is really what allows that whole process to work, which is really cool. But yes, we have a definite area. We've said that. Yes, we're finding the area. It's a definite area. Well, if we add up all the rectangles, that would give us the area underneath that curve. Good questions. All right. Take out your calculator. Let me show you. This is only to check your answer. You can't do this on the test. Go to y equals. Hurry, hurry, hurry. We got so much to do. We type in x to the third. And we go to second. Calculate. Do you see it? Look at that thing. Isn't that pretty? Isn't that pretty? Look at that. The definite integral of f of x dx is right up there. And you just press 7. And it'll draw the curve for you. You just have to make sure that the window allows you to see all, from 0 to 3. Does our window satisfy 0 to 3? Yeah. So the lower limit, we just press 0 and enter. And then it says, what's your upper limit? Well, we press 3. Enter. You can see it even draws the area for you. 20.25, is that 81 over 4? It is. No! No! You would never pay attention to the long with it, and the only thing you would ask the whole time is, why are you teaching this if I already know how to do it? Let's do the next one. Yeah, you can check your answer with that. Okay, now that I've shown you guys some of these hints, can you understand why some colleges are saying no calculators in calculus class? Because this is what kids are doing. They're just punching in, oh, well, I can find the area. Boom, done. Adding infinite number of rectangles? Stupid. I mean, come on, right? All right, so we're going to switch it up a little bit. 0 to 4. But now we got two parts to our function. We got 2x minus 1/2 x squared. And if you were to graph this, and anytime you're asked to do area, you should always be able to have a vision of what that area looks like in your brain. And for those of you who will someday take Calculus 2, sometimes we're able to find area of unbounded regions. Actually, regions that go on to infinity can also have definite area, which is, oh, it's so cool. What? In case you weren't understanding and we had to go back to it. And I would love to just reprint a set of notes and take it off for you right now, but we'll just pretend like it's not there. All right. Shut up, you dork. All right. All right. What's the width of n rectangles? 4 over n. 4 minus 0 divided by n, which is 4 over n. Very good. So now what I need to do is I need to find the x values that we evaluate the sum at. I take the beginning and I plus the width times I. We start at 0. We're starting at 0, and we add on to that the width, which is 4 over n, and we times it by I. Now, the reason why I'm showing you that, you guys, is because next time, on the next example, we don't go from 0 to 4, we go from 2 to 5. So then there, instead of a 0 there would be a 2. And that really, yeah, it gets really messy. We're going to need a lot of time tomorrow to do that. Okay. Yep, express area as a definite integral. Here we go. Definite integral is this guy. What's my lower boundary? 0, 2, 4. Function. dx. What does the dx represent? Width equals the limit. Why am I going to infinity? That's how many rectangles. The sum. What's the first rectangle? 1 to how many? N. Of the function evaluated at our spot. So the function is 2 times 4I over n minus 1/2 times 4I over n squared times my what? My width 4 over n. So I've got that parentheses there so I can multiply my width all the way through. Ask the questions, okay. Okay, so 2 is the 2 from the function. Instead of an x, we plug in a 4I over n. Minus, why? Because we said that that's the spot where we're evaluating the function. Remember, we have to do f of x sub I. X sub I represents those spots we're evaluating the function. We don't plug in 1 and 2 and 3 and 4 like I says into the function. We plug in, you know, like here we plug in 1/2, 1, 3/2, 2. So that's how we generate those spots. We come up with that expression. Question. That's delta x, my width. Delta x is my width. 4I over n is not our width. That is our x sub I. That's what we plug into our function. That's the spot where we evaluate the heights. Got it? 4 over n is our width. We've got it. Now we need to go to work. Warning. This is where you can make some mistakes. So be careful with your algebra. All right? Let's we'll write this out. Limit as n goes to infinity. Yes, you have to continue to write that. Of, yes, the sum I equals 1 to n of, what's 2 times 4I over n? 8I over n. Yes. All right, let's do this part now. What's 4I over n squared? 16I squared over n squared, then multiply it by 1/2. 8I. And we're going to multiply all that by 4 over n. Now we should probably distribute that 4 over n through, right? Okay, so now we've got the limit as n goes to infinity of the sum from I equals 1 to n of 32 I over n squared minus 32I squared over n to the third. Okay, so what makes this different than the other ones? We got two of them. We just used two different formulas. You can break summations up into two parts if you want to. No problem. You can break the limits up into two parts through subs if you want to as well. So we've got the limit as n goes. Oh, trust me, this isn't messy. Wait till you see the next one tomorrow. Yeah, we're gonna substitute. We'll run out of room there. So we've got to. We're kind of running out of room. So yeah, we got to factor this stuff out yet. So we got the limit as n goes to infinity of. We'll take out a 32 over n squared times the sum from I equals 1 to n of what goes here? I. Well, I took out the n squared. Well, we're going to get there. Is everybody okay with this so far? Okay. Then we've got minus 32 over n to the third times the sum from I equals 1 to n of I squared. We can break subtraction and addition up into two pieces with summations. You can do that. So you have this one right here. Is that one up on our board? Yep. And then we have this one right here. Is this one up on our board? Yep. So now we can make our substitutions, and then we'll work out the algebra. Well, you could write your own. See, that's the genius part about mathematical induction is that if you want to come up with your own instead, Ella Otten, which might be something you want to do. No, but I'm saying you could do like I squared plus I. Like you could write your own for I minus I squared if you want. You can figure out what that would be. All right, here we go. Limit as n goes to infinity of, 32 over n squared times, what do I substitute there? Good. Minus 32 over n to the third times, what do I put in there? All over 6. Everybody caught up? Okay, I pause. Everybody good now? Okay, limit. We're almost done. 2 steps. Limit as n goes to infinity. I distribute this n and multiply by 32. 32n squared plus 32n all over 2n squared minus 2n to the third times 32. 64n to the third. Then you're going to have a 2n and a 1n makes 3n. Times n is 3n squared. 96n squared. Good. And then you have 1 times 1 is 1. Times n is n. All over. Okay. And you can do each of these limits separately. So what can you take out of the first one? Good. We'll take an n squared out of the top. What should we take out a 32n squared? It doesn't matter. There's multiple ways to approach it. You can do it many ways. Times 1 plus 1 over n, right? All over 2n squared minus the limit as n goes to infinity of you don't have to. I'm just making sure everybody understands I'm doing the limit, kind of individually. So we're going to do that limit and that limit. You could technically write it either way. You'd be okay. What should I take out of the second one? Sure. Sure, we'll take out 32n cubed. And you have options. That's what we'll do. And I'm left with 2 plus 3 over n plus 1 over n squared. All over 6n to the third. Now, let's look. This goes to 0, right? The n squareds cancel. Left with 16. Is that cool? You just it's 16. And then this one, the end of the thirds, cancel. 0, 0. 64 over 6 is 32 over 3. Uh, 16 is like 48 over 3 minus 32 over 3 is 16 over 3, which is 5.333. Go ahead and verify it on your calculator. Look at that! Next week, I'll show you the quick way. No, you can learn how to do this by hand and just get it in a matter of minutes. I mean, it's just like bam. Oh yeah, totally. You don't need a calculator at all. All right. What? No. I'm giving you 3 homework problems to work on right now. Okay. Tomorrow we will do the one last problem, and you will continue to work on that. On Friday, actually, we might get to the shortcut rule on Friday. Oh, yes. You guys believe you don't have school on Friday. That's hocus pocus. Okay, YouTube Nation, there's your 3 problems to do. Good luck.